Good morning, everybody. Good morning, Doug. I guess I should introduce myself. Some of you don't know me. I'm Doug Kinney, here with the Getchis Wilkinson Center, and the organizer, and for most of the event, the host of the event. So welcome. You'll also want to know Sean LaBar up there, because he handles everything that I don't handle, which is 98% of everything. And Alice, are you still here? Alice is running around here somewhere. Alice Madden, the director of the center. So we all welcome you to our friendly, warm, charming place here in Boulder. For those of you from out of state, this is the right time of year, I think, to be in Boulder. 90-degree temperature, humidity not bad, sunshine. Not that you're allowed to leave the room for the next 8 hours, but it's a good time to be here. I won't go through a bunch of preliminary stuff about how I chose this topic, or I'll just say that I was worried that no one would be interested, and it was a really stupid thing for me to think that no one would be interested. Everyone is. I've been hearing from so many people over the last couple of months, oh, thank God you're doing a groundwater conference. I'm really excited about that, and so I've been pleasantly surprised by the amount of enthusiasm that I've heard for this topic. Let me see. So the program. You all picked up the program. I think it's accurate. I don't think we've had to make any last-minute changes yet, so I think it's accurate. All the talks are in this room. All the breaks and the snacks, you've figured it out already, I think, are next door. Lunch is upstairs. Pretty simple. Logistics aren't too complicated. We'll tell you if there's anything else you need to know. So pretty easy. I will encourage you in the program to look at the bios for the speakers, because I'm not going to do detailed introductions. Sometimes I do detailed introductions, sometimes I don't. Last year I Googled every speaker's name before the event to find some embarrassing, usually tidbit about them, and I thought that was really fun, but it was a little stocky, is that a word? It was a little, you go up to a line and I don't think I crossed the line, but I got pretty close. So I'm not doing that this year. I'm going to keep things, the speakers all think, oh, thank God. I'll keep things pretty simple, but the bios are worth reading if there's a speaker that you haven't met before, because there's some really interesting people here. Okay. We're already a minute behind schedule, so I better get to our first speaker. Our first session, I thought we really needed to start this event with a kind of a little background, get people up on the same page about groundwater, because at least in the circles that I run in, everyone's very knowledgeable about surface water, and then when topic of groundwater comes up, there's a lot of it's a different level of understanding, let's say. So we're going to start with some background stuff to get us up to speed. And our first speaker is Gil Barth, who's a hydrologist with Papadopoulos and Associates, which is an environmental consulting firm. It's appropriate that he's the first speaker, because he's one of the first people I heard from when we announced that we were going to do this topic. And he's provided me with a lot of advice, filling out the program, a lot of emotional support as I filled out the program. Papadopoulos is one of our sponsors. Our sponsors pay more than half the cost of doing these events, so that's a big deal for us to be a sponsor. So I'm very pleased that Gil can join us. I asked him to cover the essential science, which I guess means if you're a scientist and he talks about something that if he leaves out something that you do, apparently he thinks your work is not essential. So I'm trying to warm him up, Gil. It's tough at 8 o'clock. So I will say no more, because you're already tiring of me, and we will start with Gil, and you have his presentation.
Thanks, Doug.
I tried.
I got a clicker too. Awesome. Good morning. Thank you, Doug. I'm happy to be here. Doug didn't give you much of my background, but I've definitely been around Boulder for a long time. And it's exciting to be standing here giving this talk. I think my first exposure to this part of the campus was back in the early 90s, maybe it was late 80s, where Dr. Ernest Lack brought in David Getches to give a little bit of a talk for water law for engineers. And ever since then, I've been coming for the free food. But I'm really glad to be here. It's trying to restart the computer. So do I just, I'll say remind me tomorrow. There we go. So I'm really happy to be here. On a daily basis, I find it technically challenging and interesting to work with groundwater. I think not only the technical challenge is what interests me, but it's really looking at the socioeconomic impacts, ramifications of our management of water in the desert Southwest. It's just got a whole lot of facets that keep me interested. And so on a daily basis, I'm able to get involved with that, and it's a lot of what I enjoy. This was an opportunity for me to come speak to you and try and give you a little bit of background or set a little bit of groundwork for today's session. So I'll start off with a little bit of an overview. I will talk about groundwater hydrology, the hydrologic cycle, talk about flow and pumping and surface water connection. I'll go into a little bit the equations of flow. I won't try and belabor that too much. There won't be any tests. I ask you to try and look alert while I'm doing that, but you don't have to actually pay attention. But it'll give us, some more perspective, and we'll work through that. And then really the gist of why I'm here is to try and talk about what I consider pivotal management concepts. There's a lot of different ways we could refer to this, but what I'm hoping is at the end of the talk, you'll take home something that will stay in your memory and won't just be an equation or some artifact that will seep out. So I'll start with groundwater hydrology. I've pulled from the wonderful graphical resources of the USGS, a beautiful slide here about the water cycle. And the main reason for this slide is to emphasize that it's a continuum through time and space. We're talking about groundwater being one component of that continuum, and there are no barriers here. You don't see any depictions of barriers. There's arrows that transition from one realm to the next, and you can have transitions in terms of phase, you can have transitions in terms of time, but it's all one system. And we happen to be focusing today on the groundwater component, and for that reason, I often think in terms of a groundwater budget, that is what comes into the groundwater system and what goes out of it. And that groundwater budget will be part of what we're talking about today. But the main thing is that you don't see any walls here, there are no fences, water flows through a system. So with that, I want to jump over to groundwater flow in aquifers. We're jumping to the groundwater system and starting off with some basic definitions. An aquifer is a water-bearing permeable rock or some other material that allows water to move in the subsurface. And we have two basic distinctions there, either an unconfined aquifer or a confined aquifer. And I'll get into some of the details about that. Specifically that for an unconfined aquifer, we have something where it's essentially like a bucket. We've got some sort of material that allows water to flow through it, and the water's gotten into there probably just through a simple percolation process moving down from above, and it's sitting in there and it's not pressurized, it's hydrostatic. So if you went deeper in the water, you just have the pressure of the depth. It's a fairly simple system, and our bucket in this case is defined by a bottom, this confining layer. And it's the material in here with a hydraulic conductivity that reflects how fast things can move. And that provides our bucket and this for our unconfined aquifer. The second type is a confined aquifer. And we've got a system there where water has been forced down between a set of layers, and it can be at pressure then. It's not simply how much water is stacked above you, directly above you, but how much pressure has developed in the system. And I could go on a bit about that, but the thing I like to describe is being on a subway platform station waiting for that train, and you've got a crowd of people and you're sort of pushing in there, and then the other train transfers from the other tracks upstairs, and another 1,000 people are trying to come down the stairs. That's a confined aquifer system. You've got more pressure coming in and you're pushing tighter and tighter, and your train hasn't come, so everything's getting a little bit squeezed. So we've got two different kinds of aquifers, an unconfined and a confined system. We have hydraulic conductivity, indicating the resistance of flow. It's our basic sort of principle of what's happening in the subsurface, how to characterize the subsurface material there and how likely it is to allow flow to go towards typically a well is what we're concerned with. And then some basic statistics about groundwater on Earth. About 30% of all fresh water is groundwater, so it's not the big player, but it's a pretty big player. That's a fair amount of water. And then just some statistics on what kind of time you can expect groundwater to reside. It can be a fairly fast system where it's moving in and out in a matter of days or weeks, or it can be down there for thousands of years. So that's our groundwater flow and aquifer. But how do we typically interact with groundwater? It's what lies beneath. So it's down there. We don't get a chance to stick our hands in it much. We don't get a chance to sort of view at its beauty or marvel at its majesty or anything like that. We have limited opportunities, and they come in the form of springs, river seepage, and pumping. And I want to walk through a little bit of that and give you an idea why I've included that as part of my talk today. Starting off with springs, they're for me one of the most sort of magical manifestations of groundwater, because it's this opportunity to get a little bit of a glimpse of what's been happening underneath you. It's also usually a nice pool of clear water that your kids can splash in or something like that, and you can find it entertaining. But the bottom line is it's a small hint as to what's going on underground. I've borrowed, again, another USGS figure here, and we've got the opportunity for water to move into some sort of permeable formation and then be forced back up in the form of a spring. And a large part of what I included this figure for, or a large reason I included this figure, is to convey the fact that it's a combination of both topographic and geologic conditions that lead you to having a spring in that location. I've got favorites. I've got lots of favorites. Black Hills of South Dakota have some great springs. Bottomless Lakes in New Mexico, near Roswell, New Mexico. Montezuma Well in Arizona is another favorite of mine. And this is a Google Earth image from an area between Flagstaff and Phoenix. And it's typical desert Southwest. There's a riparian corridor, a little lush corridor of green, and most of it looks pretty barren. There's one location here that might look like an artifact, just a black dot. But if you zoom in and you look at the cars here as a scale, you realize it's something called Montezuma Well. Just as an aside, if you take the red eye into Phoenix and you're driving bleary-eyed drive in the morning from Phoenix to Flagstaff, and you look at your family and say, hey, I want to stop at the Montezuma Well, I guarantee you they're going to assume that you're talking about some casing in the middle of nowhere. But it's actually a pretty gorgeous site. And it's pretty remarkable. And I mention it because it reminds me of why groundwater is so important. It's hidden from us so much of the time. There is no clue here. Your family has no idea that you're not just dragging them out to some deserted field site, but you're showing them something that has a historic context, and it's still important to us today. It represents how groundwater is an important part of our society and other societies in the past. Water has been diverted there for agriculture for more than 1,000 years. So springs is something I love to talk about, but I'll get on to a little bit more, some additional material, namely the flow between surface water and groundwater. And this is critical for a lot of systems, especially when you consider prior appropriation and other forms of law where surface water kind of dominates everything. So if you have anything that affects surface water, then you need to pay attention to it. And we have three basic ways of water interacting with the groundwater. surface water interacting with the groundwater. We can describe it as being a gaining stream where the water levels in the adjacent material are slightly higher than the stage of the stream, so you actually have flow contributing to the stream. You have a losing stream where you have flow that the water levels adjacent to the stream are lower, so you have water leaving the stream, so you're losing water, and then you have a disconnected stream. So this is easy to gloss by, and it might be later that the only thing you remember is that he said disconnected, and that means there is no connection. So I'll throw in an analogy here. These two represent early parenting. Okay, you have a child, you are the parent, you have a child. There is interconnection between both. We learn from our children, and we hopefully teach our children. There is that connection. Down here, this is the teenage years. Okay, you can call it disconnection, but don't walk out of here thinking that, oh, they don't communicate to each other. No, as a parent, you are constantly trying to provide information, or flow in this case, to the groundwater. Okay, you can expect absolutely no response from the groundwater. So that's the delineation I want to make, and that's our surface water interaction. Groundwater pumping and drawdown. We're back to that unconfined, confined system differences. I want to just briefly go over the differences there, and it comes down to that we've got grains in both the similar aquifer, similar material there, similar pumping rate, everything's the same except for there is in this system a confining layer, in this there is none. So in the unconfined system, we have the opportunity, when we start pumping, we actually dewater the pores. We on a typical system will take 20% of the aquifer volume and be able to pull it out as water. So it's a response, because that's 20% of the volume, that's a fairly, in relative terms, a fairly slow response. It pulls out water in a relatively slow manner compared to the confined system, where the water is supplied to the well. When we start pumping that well, we decrease the pressure in the well, and it's the combination of the water expansion and the pore matrix compressing that provide the water to that well. There is no dewatering. There is no, I didn't have to, well, I didn't draw these anyway, someone else did. But somebody didn't have to draw in a little brown area here. What happens is strictly in terms of a pressure change and the opportunity for water to come out of the well. In this case, it actually is a dewatering. So we've got a fundamental difference there, and it shows up to a large extent in terms of how fast the system responds and how far the signal kind of propagates. A good way to summarize it is, if we look at this difference in the storage term, I used the value of 0.2 earlier, and we've got a range here for storativity, but the take-home point is that you could put it on the order of 1,000-fold difference. And so if we have drawdown in our confined system for that well, for that pumping rate, for that system, it's going to be about on the order of 1,000 times larger drawdown area than it is for the unconfined system. Same system, it's just whether there is a cap or some sort of barrier that limits, doesn't cut it off entirely, but it definitely limits the amount of flow. I want to take us from, and I should have pointed out that this system is very simplistic. We've got, if we did the math for this, we'd put in our equations that these are infinite boundaries going on and on towards the edge of the domain. So if we then go to a more complex system, we can talk about something where we've got recharge coming into it. We've got water flowing to a stream, so we've got recharge and discharge. If we start pumping this system, we can affect it in one of three ways. We can create the situation where there is more recharge into the system. We can be pulling more water into the system. We can decrease the amount of discharge so that there's less opportunity for water to go to the stream. Or we can remove water that is stored in the system. So we've got changes in recharge, changes in discharge, and pulling from storage. So three categories, but two of them get lumped together and have been defined as capture. So that increased recharge, how much more might be pulled into the system? I should point down to one of these where it's pumping. How much more is pulled down into the system? and how much less is discharged. Two of those are put together as capture because they are going outside of the aquifer. They're going to our water budget and pulling water in. We're not dealing with just aquifer water. It's the storage term that is just the aquifer water. And we'll work on this a little bit more as I move forward here. But it's a key distinction that there is capture, which is being pulled from somewhere other than storage, and there's storage. So I'll go into the equations of flow, but not for long. So Darcy's experiments. Darcy was in the late 19th century. He had fun. Well, I'm conjecture. Sorry. He did a lot of experiments with aquifer materials, and he created with this series of experiments, for instance, putting aquifer material in different lengths of tubing, and then putting a different driving force. So this is water here, these lines, putting a different amount of driving force through that to drive water through that aquifer material. He was able to come up with a fairly simple relationship. That is that the Darcy velocity, a measure of the flow coming out of the system, is related to the hydraulic conductivity, which I've already mentioned, sort of the resistance of the system, the potential difference. So in this case, it would be represented by what is the change in water levels from up end of the column to the down end of the column, and the distance. So you can play with it. If you double the height and you keep the length of the aquifer material the same, you're going to double the speed that it goes through. Have the length and keep it the same, you do the math, you're still going to double the rate of flow. So we have those basic equations. People did more sand experiments. They had fun with it. They took that water level and put it the same water level across the series of tubes and let the tubes drain out at the bottom with the aquifer materials in each of the tubes. So as far as that force, you have the same force going through those tubes, but you have a different length of travel. And so you can do the math. You can do the math for a different length of travel, and you can see that you're essentially going for a flow that's called the value of 1. This flow rate would be half of that value because it's twice as far as it travels. So some nice basic math. That's about as far as I'll take you with the equations. There's a concept here that's inherent in this that sometimes I've seen get confused in actual cases where we're looking at this and the water's flowing vertically. And people talk about water flowing, it's gravity. Gravity makes the water flow. Gravity results in a gradient. Gradients have directions, though. And this direction is along the length of that tube. In this tube, water cannot travel vertically. And so don't forget that if you're looking at some mountainside or some aquifer somewhere, if there are constraints in terms of a confining layer that's formed some kind of tube, you're going to have water that doesn't necessarily travel straight down. It might travel along a path that's not straight down, even though gravity still works straight down. An example of that in a real-world situation, which I won't go into any details except that to say that we have water piling up here due to recharge and working down through the system, and it hits the highly permeable layer here called the Grand Rapids. At that point, there is enough pressure that it can discharge in this direction to a lower pressure, or it can discharge to that face. So you actually have water flowing uphill here. Pressure can force water to flow uphill, and I've heard that's true in the legislature as well. You can take Darcy's law and you can do a lot with it. We can divide by the porosity, and we can have an equation for velocity, and we can start doing equations in 3 dimensions for transports, reactions, sorptions. We can do all that. So the question is, if we've got all those governing equations, if we've derived all that, why do you have to sit there and wait for me to come up with an answer for you? Why can I not just give you an answer in a day? Hey, Gil, where's the water going? How long will it take? It's because of complexity. Because what lies beneath, we don't have fully characterized. We don't know exactly what's going on there, and we have to take estimates based on looking at what's coming out of a spring. We have to take estimates looking at what we have from a borehole. And in addition to just characterizing that spatial uncertainty, we have uncertainty in terms of the water budget components. We don't necessarily know exactly how much of the water is percolating all the way down to the groundwater. It's pretty difficult to characterize how much a phreatophyte is consuming when it's trying to tap into the groundwater and how much of the groundwater it actually intersects. So it's that complexity that definitely limits us. So I think I've still got enough time for my pivotal concepts. I debated a lot on what to call these, key issues, take-home messages, whatever you want to call them. They're what I'm hoping you'll retain later in the day or even tomorrow. Aquifer size alone is not informative. I could have played with this and tried to shorten it up, but I tried to keep it relevant. Groundwater provides a line of credit, not a savings account. There's an analogy that I like to get into, and I preach on that virtually endlessly, or it feels endlessly. And depletion can be a long-term commitment. So you can see here that I have my tendency to be right on the cusp of getting into or actually invoking analogies, and you can do some of your own extrapolation if you want, but I'll try to go through my example. One of my first example. We'll start with a deep, thick aquifer. This system, what I'm representing is an unconfined system. We could go through the figures if we had time and do it for a confined system as well. Well, we've got a deep, thick aquifer. My graphical skills are limited, so I've got my vegetation here, I've got recharge, I've got a stream flowing across it. So inherently, there's interaction with this aquifer, just like in our hydrologic cycle, the nice graphic from the USGS. My simple one still has underlying, probably discharge from the stream to the aquifer and the up gradient end of the stream, and in the down gradient end, probably some recharge back to the stream. And we've got recharge from precipitation. We've got plants that are pulling up soil moisture from the groundwater. So what happens if we start pumping? We cause a certain amount of drawdown, and the question is, where does that pump water come from? Is it from storage? Is it from capture? Well, inherently, it's virtually always from both. We've got both storage and capture going on. So we've got a system where you're not just talking about what was in this aquifer. We started with this context of a deep, thick aquifer. Oh, that's our savings account. Let's just pull water out of there. As soon as you start pulling water out of there, you're capturing as well. You're changing how this river loses water. You're changing how that river gains water. So you don't have a bank account there. You don't have a savings account. You've really got something that's closer to a credit card. You've made a purchase, and you will have interest and fees on that, or some, we could spend time on that analogy a little bit more. But the main thing is, it's not just a savings card. I mixed them. It's not just a savings account. It is a credit card, and there are costs involved. As you go ahead and pump more, you have additional effects that go on with time, and we've drained some of it, and I've tried to provide in my graphic here, but I don't do a good job of representing the shape of it. But you have drawdown that's more localized, that's more in the vicinity of the well and less at distance from the well. So you've created a signal not only in time, but in space as well. And after you stop pumping, you still will have effects that persist with time. So you can continue, even after you have stopped turning, the pumping should be turned off now, but it's not. Graphical skills cutting in there again. When you've turned off the pumping, you still will have that signal propagating. You still have storage here that's been depleted, that's been evacuated, and you still have a system in terms of capture that is different from what you started with. So you still have that interest payment going on. You still are carrying debt long after you finished your purchase. It won't be until this recovers fully that you can go back to that initial system. We can debate about whether you need to be back at that initial condition or not. But the bottom line is, you're carrying some sort of, you're you are propagating some sort of impact further in time, long after you've done pumping. It's not just that, oh, look, the spring flow is decreased. We're going to turn off our pumping well, and the spring flow will recover. No, there are people who have enjoyed writing papers about how long that impact will perpetuate, and the fact that your spring flow will actually even, in many circumstances, even continue to decrease for years after you've turned off your pumping. So all of this to belabor the fact that it's not just a savings account, it's a credit card. So I'll walk you through one example. Shoemaker, a specific example. Shoemaker wrote a paper back in 2007. He was looking at the middle Rio Grande, and he wanted to know, well, we've got a big aquifer there. What if we did somehow dewater this big aquifer, hundreds of thousands of acre-feet of water, just in storage sitting there? But we set it up so that when we pump that groundwater out, we're doing the math and we're accounting for how much we're changing our capture. And we put that water into the river. So we know we have to do that right from the start. And we could so if we start pumping, we dewater, we change our capture, we do that. And right from the start, we're going to have this curve that represents how much we're depleting out of a 100,000 acre foot pumping rate. You know, it's a whole well field. Wrong button. How much of that we're actually needing to be, we're actually pulling directly from the stream. How much of that is captured from the stream? And this exercise then goes through a process that I'm going to curtail a little bit for the sake of time. But the bottom line is, you evacuate that storage, you've got, let's say, 1 million acre feet of water that you were able to mine, and I'm using that term loosely, you pulled it out of the ground. But in the meantime, you've changed your system so that your stream leaks differently now. And there again, I should have used something like seepage, or changed the capture to be consistent with the terminology I've been using. You've changed the capture. So while you're pumping, you need to be putting water into the stream. So we can do that. We can crunch the math and figure out how much water, we can put on the farms and how much of it will sink back down, and what's the net amount that we need to, the net amount that we have that we could use for crops. And we can see it drops from 100,000 acre feet. And this is in years, that's 100 years out there. And we're dropping down. So for a long time, you can keep pumping. And you will have a decreasing amount of water available. And it's all because you decided, well, we wanted to grab hold of that 1 million acre feet. And you can set it up. And John Shoemaker even went through the math of, okay, well, what if we did the finances? What if we set up money so that the one field could pump in perpetuity? Because remember, once you stop pumping, the effect is still going to be there. And you still need to be moving the water from here up into the river because you've created this blank space in between. It's an interesting exercise, and to me it raises as much, I guess, sort of ethics question about, do I want to set something up that has to operate in perpetuity? But it's interesting to me because it drives home the fact, once again, that size alone is not the only question to answer. How am I doing? I guess I will say that we can look at, we can do some math, and we can look at changing systems from a surface water delivery, where we're constrained by what is the runoff in the system and what is the stream canal network that we can convey water to the system, and using groundwater pumping. And I'm giving you the abbreviated version as a slide. I apologize. The main thing is that with pumping, we're not limited to the runoff timing. We're not limited to runoff times, runoff amounts. We're limited to what can be pumped, but not the runoff amounts. We have the ability to extend our season and potentially increase acreage. And if you do those kind of transitions from surface water to a groundwater system, you need to carefully keep those in mind and do all the math. It's certainly a good credit card, and as a tool, groundwater can be a remarkable resource, but I want to emphasize that it is akin to having a credit card in your pocket. You can change the timing of the system, you can draw on it, you can use it effectively, and you can manage it in an intelligent way, or you you can end up deeply in debt and not really see any way of getting yourself out of debt. I think I will just say, let's see, aquifer size alone, I just said that recently, and the fact, well, depletion is a long-term commitment, I'll just state that again. So I think I'm out of time. Thank you.
Take a question or two if you.
Oh, great. Yes.
Have you looked at the Denver Basin aquifers, given your models?
I have not worked specifically on Denver Basin myself, a little bit with some storage potential in the northern end of it, but not as a water supply system as a whole. Thanks, Doug.
Thank you. I always like when we can weave in a little science, a little equations into the presentations here. I just feel that this, the law school has it's like the immune system tries to kick that stuff out sometimes, but we push it back in. So that was a very painless way to get science in the agenda here. Thank you, Gil. All right, up next is Lenny Konikow. Konikow, right? Am I getting okay? It's funny because if you start doing research about groundwater, you see the same name come up again and again and again because all these great USGS reports over the years, it's just a tremendous publication record. Lenny's what do they call you? Emeritus scientist? That's what they're calling it with the USGS. For a long career there, as I say, publications everywhere. I'm reminded of the Ron Burgundy quote that he's kind of a big deal. You see the name everywhere. I've given him, I think, what is a nearly impossible task is that I said, why don't you summarize for everyone where the groundwater is in the West and where it's being used and where it's a problem and what issues and what areas look to be a problem in the future and do that in 25 minutes, 25, 30 minutes, I don't know if it can be done, but I'm anxious to see, but maybe you're not going to have 25 minutes. We're having an issue here. Well, I'll let you, hold on a second. The start of a conference is where you work the bugs out here. So. Yes, you're going to have to restart. We're just going to have to restart the whole thing, if that's all right. For the video that we're shooting here. Okay. All right. Looks like we figured it out. Okay. All right.
Thank you very much. I appreciate the invitation to speak here. And the only personal note I'll add at this point is that it's a pleasure to be back in Colorado. I started my long career with the USGS in the summer of 1971, working with the USGS, and came back in 72 and been with them for the rest of my career. And what I'd like to do today is try to meet the challenge that was given to me and talk about groundwater in the West with a little bit of a touch of a national and even global perspective, but I'll focus on the West and Southwest. Okay, well, I can't figure that out. What do I push?
Can use this one for now. No.
This too much science.
Okay, well, a little bit of a technical glitch here. The slides won't advance.
Just the little thing, little piece that goes. Yep, there it goes.
So what do I push?
That one advances.
Okay. All right, we're back online here. Okay, so we're going to look back at the so-called good old days, maybe 100 years or so ago. Wells were few and far between, generally hand-dug, very primitive pumps. Well yields were pretty low, and issues of depleting the groundwater resource just simply were irrelevant. There was so little pumpage that it just didn't matter. There was no interference between wells and streams or wells and other wells for the most part. Well, today we have powerful drilling technology. We could drill deep wells in a matter of days. We have very powerful pump technology. We could remove a lot of water every minute from the ground. Most of the pumping in the U.S. and actually globally is used in irrigation, in the agricultural world for irrigating crops. That's probably 70 to 80% of all groundwater use is for irrigation. So we can ask, we're pumping just enormous volumes of water. Where is it all coming from? What's the source of that water? And we could look at it in terms of a balance, in terms of a scale, okay? And I'll reiterate some of the points that Gil made in the introductory talk. Under natural or pre-development conditions, recharge to groundwater systems is balanced by discharge from the system. There's an equilibrium, a kind of steady state in the system. There's flow through the aquifers, but the recharge and discharge are balanced. Once we start drilling wells and pumping the aquifer, everything changes. Now, we've increased the discharge from the aquifer system through these wells, and that discharge has to be balanced by some combination of a change in groundwater storage, a change in groundwater discharge, and or a change in groundwater recharge. These three factors, some combination of those must balance the well discharge. One of the things to note is that the natural recharge to the system does not enter into this balance. It's really irrelevant. And there's a lot of people who kind of overstate the value of knowing the natural recharge in terms of setting limits on or managing groundwater discharge. So as Gil said earlier, the change in groundwater storage we could refer to as storage depletion or just depletion, and the combination of change in discharge, change in recharge is very commonly just lumped together and called capture. There's also a timing to the distribution or balance of factors that balance the discharge. Okay, and initially when you turn on a well, 100%, all of the water that's being removed by the well comes from a depletion of groundwater storage. But over time, that fraction of the pumpage derived or balanced by storage depletion decreases, and the fraction or percentage derived from capture will increase over time. Okay, and I don't give you a specific scale on this because that will vary depending on the properties of the particular system, the location of the well, distance from surface water sources, and so on. But eventually, the amount removed from storage as a fraction could approach zero. Once it reaches zero, the implication of that is that there's no longer any changes in the water level or water table. Okay, there's no more drawdown, and the system has reached a new equilibrium, and all of the pumpage is being balanced by capture. And this can happen, and has happened. In many areas, the bulk of the capture consists of streamflow depletion. Okay, and that's of great concern. I mean, there are other possibilities. The capture can affect springs, can affect wetlands, it could affect discharge in coastal areas. Capture can also capture evapotranspiration. As you lower the water table, it could actually reduce the evapotranspirative losses from that aquifer. That's another type of capture, okay? But it's generally not as much as surface water capture, and streamflow capture is a major concern, and it derives from a combination of induced infiltration, which is a form of increased recharge to the aquifer, and reduced groundwater discharge or base flow, water seeping back out into the stream. Because it affects the stream and under the legal system in many states, this effect of pumpage on stream flow or on stream flow depletion can have many legal ramifications. As I'm sure you know, there have been a number of Supreme Court cases that have addressed this issue and this problem. There's a classic paper by Tom Winter and others on groundwater and surface water, and he calls it a single resource. And I think this is a very good subtitle to this paper, not to think of groundwater and surface water as separate components of the hydrologic cycle, but one that's intimately interconnected. It really constitutes a single resource. He estimated in this report that on the average, about 50% of the total annual stream flow consists of base flow, of groundwater discharge. Obviously quite variable depending on the nature of the system, but on the average it's about 50%, and that surprises a lot of people. There was a recent study looking at the upper Colorado River Basin that analyzed base flow and stream flow and came to the conclusion, which also surprised a lot of people, that 56% of the stream flow in the upper Colorado River Basin originated as base flow, as groundwater discharge. This is perfectly consistent with the earlier studies of Tom Winter and his colleagues. In terms of storage depletion of aquifers, of groundwater depletion, there's two ways to characterize the depletion issue or problem, two ways of measuring it, two ways of characterizing it. One in terms of water level declines, and this is what people using wells measure. This is what they see. This is the impact that affects them. If the water level drops below their pump intake, they've got a major problem, and they know that. Okay? The other way we could characterize it is in terms of the actual volumetric loss of water in the aquifer system. So I'll talk briefly about both of these, talking first with a few examples about water level declines, because this is what's easiest to measure and easiest to see. The USGS did a study of this, 10 years ago it was published, and basically they show that substantial water level declines, more than 40 feet in wells or more than 25 feet in unconfined aquifers, are pervasive throughout the entire U.S. And maybe a little more common in the western U.S. We could see how this is manifested looking at an observation well in Las Vegas Valley. And here from the over a period of about 4 or 5 decades, we see a water level decline on the order of 150 feet. And this is quite significant and quite concerning. A break in the trend in the 1990s, which coincides with importing greater quantities of water from the Colorado River, and also with some water management policy changes that encourage conservation. And so both of these together did have an effect. We could look at the correlation between the water level declines and population growth, and there's definitely a strong relation, as you would expect. We even see around 2005 to 2008, a little kink here related to the economy and other factors, and actually that seems to correlate with a response in the aquifer. Okay, also not very surprising. We could look at some springs. In this case, also in southern Nevada, just to illustrate that groundwater pumpage not only affects streams and streamflow depletion, but also can affect springs. And here we have a long-term record at a couple of regional springs. And what we see is where pumping started around 1913. With the limited observations they have of flow, there is a definite downward increase. One of the springs dried up in the late 50s. The other one dried up in the late 1970s. And this is not an isolated example. It's just one from the Southwest, but this is seen around the world. So let's take a look at the other way of characterizing groundwater depletion in terms of a volumetric change. And I did a study over many years, finally publishing it in 2013, looking at very long-term changes in storage from 1900 to 2008 in 40 major aquifer systems throughout the U.S. Okay? And this is what we see. The hatchet areas are areas where one aquifer overlies another deeper aquifer. So we're trying to show what the depletion volume is in those systems. There's the Denver Basin right there. So in terms of groundwater depletion, the most serious, well, let's say the largest volumetric depletion is in the High Plains Aquifer, shown in red here. Okay? The Mississippian Bayman Aquifer, where there's a lot of irrigation for rice and other crops, is actually the second largest volume of depletion in the U.S. Southern Arizona, Central Valley of California are number 3 and 4 in terms of volumetric depletion. Okay? In the humid East, there's still some depletion. It's measurable. Not as much. There's so much more potential for increasing recharge in the East, so that that balance will come into effect quicker. What we could note is that there's two systems. They're actually by volcanic rock aquifers in the northwestern U.S. where there's actually negative depletion. Okay, and what that means is that the water table is higher today than it was before any development. The reason for that is they've imported and diverted surface water for irrigation, apply that water on the land surface, some of that infiltrates, that becomes recharge. That they have increased the recharge above the natural rates substantially, and so the water table rises. Okay, and those two systems are kind of unique in the U.S. for now, but in both of those, and I'll show you in a couple of minutes, the trend has changed in the last couple of decades. And now they're, even though they still have a surplus of groundwater relative to pre-development conditions, it's on a downward trend. It's being depleted because of drilling additional wells. So we can look at the trends over time. Again, focusing in the Southwest, in Arizona, what we can see is a real acceleration following World War II as drilling and pump technology increased substantially. Irrigated farming, irrigated agriculture took off, and this was really accelerating to a total of, by 1980 or so, 100 cubic kilometers. This was also creating some problems of land subsidence, which was getting serious. In 1980, Arizona changed their water management policies. They changed the law. This seems to have had an effect pretty quickly. And I see on the program tomorrow morning we're going to hear a talk about Arizona, and maybe we'll hear more about the relation between water use and water policy and water law tomorrow morning. But things kind of stabilized for maybe 20 years or so, and then there seems to be, at least on the average, an increase in depletion continuing today. In the High Plains Aquifer, again, the largest volume of a single aquifer probably anywhere in the world. If we look, it's one aquifer system, but it's not a uniform condition. What we can see is that the problems are much worse in the southern High Plains. Nebraska, in terms of the volume of depletion, really has very little problems. They have some areas where water levels have risen. They're sitting on a very thick aquifer with good quality water, lots of reserves in Nebraska, whereas in Texas and Oklahoma, we have water level declines since pre-development time, 1930s, 40s, so on, exceeding 150 feet. What that means in some of these areas, they've actually dewatered more than half the saturated thickness of the aquifer. That trend is simply unsustainable. That cannot go on. Okay? It's not going to happen in one day, but this has evolved over 60, 70 years. It can continue, and it seems to be getting worse. So it's going to have major impacts. In terms of the volume of depletion, in the 20th century, they lost over 240 cubic kilometers of water. By 2015, this had increased, the depletion volume had increased to 400 cubic kilometers. Just for comparison, that's about the volume of water contained in Lake Erie. So they've drained Lake Erie out of this aquifer in a period of 6 or 7 decades. You look at the time trends, again, after the end of World War II is when we saw this major break in slope, and that's when the problems of depletion really accelerated. And what we see, there's a few little kinks here, but what's most disturbing is that this is a pretty linear trend. Even up through 2015, it's continuing to grow at about the same rate. Okay, and this is disconcerting. I don't know how much longer this could go on. I'm surprised it's gone on at the same rate for so long. At some point, this has to begin to stabilize. Okay, but it hasn't yet. The data don't show that it's stabilizing yet. Why? Well, we could look, for example, at a Landsat image from southwestern Kansas. And what do we see? Each of these little circles is a center pivot irrigation system. The little circles have a diameter of 1/4 mile. Each one of these is supplied by a well. They're pumping like hell out of this system for a very dense network of wells. And when you see areas like this, you say, well, it's no wonder they're draining the High Plains Aquifer. You could see the effects on streamflow in western Kansas. This map, produced by the Kansas Department of Agriculture, all the red dotted reaches of streams are streams that were perennial, permanently flowing in 1961 that have now become intermittent, that are no longer permanently flowing. All throughout, even the main stem of the Arkansas River has fallen into this category. And the main reason is pumping from wells. Now, we could look at the depletion volume in another way. One thing to consider is the size of the aquifer. because the High Plains Aquifer with the highest volume of depletion also is the largest in size, the largest in area. So if we normalize the depletion volume by the size of the aquifer, what we see, what stands out is that this is since 2000, what stands out is the aquifer with the most serious problem per unit area is the Central Valley of California. Actually a much more serious problem than the High Plains in terms of what I call depletion intensity, accounting for the size of the aquifer. We see that in this time period, those two northwestern aquifer systems now have positive depletion. Okay. Things are a little more stabilized in Arizona. Basically, things are much more uniform in terms of depletion intensity than in terms of depletion volume. If we look at what's been going on in the Central Valley of California, what we see here, the red line is groundwater storage changes from the early 60s through 2014. Characterized climatic conditions as dry or wet, dry, wet, variable, wet, dry, wet, dry. What we see during the dry periods, there's less surface water available. Farmers are pumping more, they're drilling more wells, they're pumping a greater fraction of the time to make up for the lack of availability of surface water. That causes an acceleration of storage depletion, water level declines. During wet periods, pumping is reduced and there's a recovery. Dry periods, it goes down, wet comes back up. What we see is that the recovery during the wet periods is not nearly as much as the drawdown during the dry periods. So again, there's a pretty consistent trend of depletion continuing over time. Particularly in the southern part, the San Joaquin Valley, southern part of the Central Valley, we also have a problem of subsidence. And what we see with subsidence, and this land subsidence, differential subsidence, when you're talking about a major network of canals, you don't want the slope on those canals changing because of land subsidence. That gives enormous headaches. What we see is that during drought periods, when pumpage increases, subsidence increases. During the wet periods, unlike the water levels, there's no recovery of subsidence. That's basically a one-way process. Okay, it's inelastic. Wet periods, it stabilizes, but no recovery, or very little recovery. Then in a drought, subsidence increases. So the subsidence is a continuing, ongoing problem, especially in the Central Valley. So we could look at one of the two volcanic aquifer systems, the Snake River Plain in Idaho. Long-term record shows increasing storage, that is negative depletion, through the 1970s, at which time more and more wells were being drilled, and now we're on a trend of increasing depletion. It still got a long way to go before we get back to the pre-development volume, but it's headed there, with a similar trend in the Columbia Plateau aquifer system in Washington. Another way to look at this, kind of getting back to some of the issues Gil talked about, pumpage is balanced by storage depletion and capture. Well, how much can be attributed to capture? How much could be attributed to depletion? How does this relate to the pumpage? Well, we could non-dimensionalize this and develop a depletion fraction, which is equal to the depletion volume divided by the cumulative pumpage. Okay, and again, that would be related to the capture fraction, would be the complement of that. Well, it turns out in the United States, for a period of 1950 to 2005, we have good data on the total groundwater use, and we have the estimates of the total groundwater depletion. And this is a little surprising to some people. The depletion fraction is actually only 0.15. 15% of the total withdrawals is balanced by depletion, which is not to say depletion is not a serious problem. It is. But the other side of this coin is that 85% of the pumpage is balanced by capture. And if you have senior rights on a stream, this is what is going to affect you and bother you and concern you more. We look at the depletion fraction in selected aquifers in the U.S. We see it's highly variable. The highest depletion fractions from 0.8 to 1, that is where most of the pumpage is balanced by storage depletion, comes from those aquifers in the southwestern U.S. in very arid climates with very little surface water available. In other words, there's no water to be captured, essentially. So it has to come out of storage. We could look again at the Central Valley of California as being somewhat typical, but it's a little surprising to some people that this reflects the national averages on the whole, and it hasn't changed much in time over 4 decades. About 85% of the withdrawals are balanced by capture. Only 15% balanced by storage depletion. Because in the Central Valley, there is surface water. There is surface water available to be captured. And so it is. We look at the trends in the U.S. for the total. This gray line shows the total depletion in the U.S. and some of the more significant contributors. Again, what's concerning is that this trend since the 50s doesn't seem to be leveling off yet. In the 20th century, by 2000, 800 cubic kilometers of water depleted out of groundwater storage. That's 2 Lake Eries for the whole system. And what is really concerning is that in the next 8 years, that increased by 25%. It took 100 years to reach 800, and then just another 8 years to increase 25% above that. Okay. The trends are not encouraging. We can look globally. The data are a little less certain. It's a little fuzzier making these estimates, but we nevertheless did. We have data from several large aquifer systems, and the total by 2008 was on the order of 4,500 cubic kilometers. Globally, the volume of groundwater being depleted is large enough that it is actually a measurable contributor to sea level rise. From 2000 to 2008, if you look at the steepness of this line as a reflection of the rate of groundwater depletion on the continents, the great bulk of that water eventually winds up in the oceans. That's the ultimate sink, whether it's a pathway through the atmosphere or through surface runoff or whatever. Most of it ultimately winds up in the ocean. In this 8-year period, the rate of groundwater depletion can explain or balance 12 or 13% of the observed sea level rise. A small but non-trivial contributor. Okay? And this was certainly a surprise to most of the climate scientists studying sea level and sea level rise. The whole issue of groundwater depletion brings into question the sustainability of groundwater use, and there's a lot of groups analyzing this and publishing their results and their analyses on sustainability and water security. There's even been a few studies looking at the role of water stress on instability and conflict. Okay, and this is a concern. It's debatable how much this really happens, but there are certainly 2 factors contributing to water stress, Increasing groundwater depletion is certainly one of them, and climate change is another factor. And the general consensus among scientists is that climate is changing. That's what the data show. And it's having an effect on hydrology. And in fact, there's been a recent publication by a very esteemed group of hydrologists and hydrogeologists looking at the implications of projected climate change for groundwater recharge in the western United States. So we are well aware of climate change, and we are trying to figure out how it might impact groundwater resources, as well as other hydrologic resources. So it's on the radar scope. So the future. Okay, that's always a good question, and it involves some speculation and some educated guesswork. But I would guess that growing population is a significant mark of the future, and that will yield increased demands for food and water supply. And in fact, the growing population is one of the driving forces for groundwater depletion. Climate and hydrologic systems are changing. Okay? And hydrologic systems are changing partly because of changes in climate, but partly in response to man's activities. So in response, there are two things that need to happen. One, we need improved water management, improved water policies to help deal with this. It probably won't be enough. We are going to have to adapt to these changing hydrologic and climatic conditions. And that can take many forms. So in conclusion, I would say the evidence is clear that groundwater depletion is growing in the western U.S., in the U.S. as a whole, and in the world as a whole. Because of this, sustainability of the present groundwater use is clearly at risk. Things cannot go on indefinitely the way they are today. Groundwater and surface water are interconnected and really should be viewed as a single resource. On the average, most groundwater withdrawal is balanced by capture, less is balanced by storage depletion, but the storage depletion is indeed part of the problem as a consequence, an impact of the groundwater development. Clearly, pumping and depletion can cause a number of detrimental environmental effects, including land subsidence, drying out of wetlands, drying up of springs, and streamflow depletion. It's clear, and there's some evidence to support, that innovative water management actions, changes in policy, can clearly help mitigate the problem. It may not be enough, but it will definitely help, and is certainly advisable. So, water policy and legal framework may need to be modified to facilitate optimal water use, better conjunctive management of groundwater and surface water, as well as sustainability goals. Always keep in mind, no matter what we do in the legal framework, Mother Nature takes precedence. Okay? The laws of nature will override the laws of man. Economics have a strong influence on how people behave. Our greatest groundwater users are in the agricultural community, and they are very responsive to economic stress. Okay? And so what we're going to see, what we have already seen in areas where depletion is significant, water table declines are large, farmers stop pumping. They have a choice. They could drill deeper wells, they could put in more powerful pumps, or they could get out of business and go to dry land farming or sell their land for some other use. This is happening particularly in Texas and Kansas. Okay? And as depletion continues, water tables decline, that economic impact and dislocation can spread to more areas. So with that, we'll bring it to a close. Thank you very much.
Wait,
me get you the mic so we can pick it up on the video.
Thank you for a really terrific presentation. And I was struck, and I would like to see if you would agree with this, that the groundwater pumping activity really obviously starts post-war, but it also seems to be starting with the more globalization of the food system and free trade agreements around agricultural products. And I wonder if you know of anyone who's done work looking at those two relationships.
I'm sure somebody has. Off the top of my head, I don't know who, but you know, I would think somebody has looked at that, but I can't think of who at the moment. So. Mike.
I'd like you to comment on, oh, I'm sorry. Could you comment, I was very interested in the 15 versus 85% and balancing the well pumpage. Given these large regional aquifers, do you see a scenario with climate change which affects the spatial and temporal distribution of recharge and precip? Are some of these places on a sort of short term, it could go from 15% to 50% over in a decade or in 5 years? Are they on that kind of a vulnerability cusp?
Well, you know, climate change will impact this balance that we have, because if you go into areas where there's increased recharge from increased precipitation, that will offset the pumpage, that will reduce the depletion. You know, even without climate change, we have wet periods and dry periods. We have droughts and wet cycles. And these show up in the water level. Like we see in the Central Valley of California, you know, 2 to 5 year cycles of wet and dry. Climate change may accelerate that. I think the general thinking in the Western U.S. is that, at least for the next 50 years, the wetter areas will get wetter, the drier areas will get drier. And if you're in one of those drier areas, that means you've got even more problems. You better stop there. Yeah. Thank you.
All right, thank you. I'm pleased that you concluded by talking about in the future we need improved water management. You said, you know, maybe better legal frameworks, maybe a better use of economic instruments, basically the whole suite of things that fall under the category of governance. We're going to need better governance. And so that's kind of where we're transitioning, not only in this opening session, but really in the remainder of this event primarily. We're talking about how people govern water resources. And so to get us on this transition, we have Sharon Megdal, who is with the University of Arizona. Like a lot of people in academia these years, she has a dozen appointments and things at the university, but I guess I think of your primary affiliation as the director of the Water Resources Research Center. Maybe I just think that because I've always been fond of that center, because that's where I defended my dissertation. So. Sharon has worked all over the world on groundwater governance issues, and there's a tremendous variety of approaches, and there's generally not a lot of, there's a lot of struggles, I'll just say that. So Sharon, why don't you take it over?
Thank you, and good morning, everybody. And Doug, thank you for the invitation to speak today. And going to feel a little bit like Monty Python, and now for something completely different, because we are going to transition from the more scientific and physical to the legal. And many of you maybe have seen that slide, the hydrologic cycle, you know, and so this is where the law doesn't necessarily recognize the physical systems, and we'll talk about that a little bit. Doug assigned me this title, and I wasn't astute enough to say, hey, Doug, I don't think I want this title. Give me a different title. But I didn't realize that until it was too late. The program had been published and all that, and I thought, well, if I'm going to use this title, and I've seen this term, you know, secret, occult, and concealed resource, but I didn't really know that much about from whence it came, so I had to do a little research. And how many of you in the room are lawyers? You know, this is, I think, my only legal citation here. But it does come from an 1861 case, and I read articles about it. I actually didn't go and read the case. But Judge Brinkerhoff states, and this is, I guess, known as the doctrine of the biggest well. I think that's what came out of it in terms of the analysis of it, is that because of the existence and movement of this water underground is so secret, occult, and concealed that any attempt to administer a set of legal rules is practically impossible. You know, so you can't do anything with this, and that's where that came from. And then that was in 1861, and then there was another Ohio decision, Klein versus American Aggregates, in 1984. And I found an analysis or mention of this in an article that was in a collection of papers by Ramon Llamas, who's a very well-known Spanish hydrologist, hydrogeologist. I imagine some of the hydrologists in the room know him. I've seen him speak. And that he said that scientific knowledge in the field of hydrology has advanced in the past decade to the point that water table and sources are more readily discoverable. This knowledge can establish the cause and effect relationships of the tapping of underground water. This is in this 1984 case. But then Llamas notes, and just read what I highlighted there in red. For many people, groundwater issues still continue to be something secret, more related to water witches than to engineers and scientists. So, I mean, he wrote that, you know, just over 10 years ago. So this whole thing of this invisible water and what to do about it and how to govern it really has been and of increased interest, it's growing interest on the part of many, including the hydrologists and hydrogeologists. And I have a picture here of one of the reports that came out of a multi-year international effort led by the FAO, the Food and Agriculture Organization, which I'm sure has probably done some of the kinds of studies that was just, you know, asked about in the last question. And the International Hydrologic Program at UNESCO and the World Bank got together, and they wanted to identify best practices. And then the OECD, the Organization for Economic Cooperation and Development, about not that many years ago, 2013 maybe it was, maybe a little later, started this water governance initiative that's not only about groundwater, but of course includes groundwater. And they've been looking at principles of effective governance. And then a couple organizations here in the US, national organizations, the National Groundwater Association and the American Water Resources Association, teamed up for a workshop on the invisibility of groundwater and came up with some principles for improving it. So I put that all up there to say this is a very important topic, and it's of interest at all levels when you think about geographic scale. So I was involved in that FAO UNESCO effort in the early stages when they were holding regional consultations, 5 of them around the world, and they would invite people, practitioners, officials, academicians in to talk about their experiences with groundwater and groundwater governance. And the last one of them was going to be the one including the US. And repeatedly, you would see pictures of the world that looked like this. Now, not all global maps that people put up about water stress and the like look like this, but many of them do. And what was notable and disconcerting to me was that the United States was painted the same color. It was an average. And we know there's so much variation in situation in the US. And so I had the opportunity, and I took it, to try to convey to these global practitioners and others that you can paint the United States that way. So what I did was I started an effort, a survey effort, and I'll talk about the results a little bit more, to basically drive home the point that you have a mosaic of situations in the United States, and then even within states and within regions within states. So this comes out of the USGS does this water census every 5 years, and they look at various things, and there are data about the percent of human needs met by groundwater using, this is based on USGS data, and you just see it's different colors, different states. And then when we started looking, and I'm going to come back to this slide in a few minutes, we started asking some questions and started mapping answers and looking at results. And you see that you have different situations across the states. And then within a state, of course, I'm from Arizona, so, I have lots of Arizona maps. And this is one that shows different colors depending upon where we have groundwater management or some lesser control over groundwater pumping by irrigation. And then within, again, the state of Arizona, you have different situations because you may have tribal nations that have sovereignty over water rights and the like, and so you may have different situations there. And then, of course, I put up the map that we're all familiar with of the Colorado River Basin, looking at, again, we know we have different situations. You may be in the physical watershed, but using waters outside of it. So, we have lots of different situations. And then I decided to put this as a water map poster that we produce at the Water Center. This is our version 4.0 that was released just a year ago. And you can see on the right side of it, there are, I hesitate to, that is the right button. There are these little maps that have other information. And this is a blow up of this one here, where it shows within the state, we have different groundwater basins, and the reliance on groundwater, this teal color is over 75% reliance on groundwater. And then you have areas that are mostly reliant on surface water, and then you have others that are mixed. So the point is it's very, very hard to generalize. So let me, we didn't coordinate here, but you did a great lead-in for me in your last few slides when you were talking about your conclusions, because some of the things you talk about as your conclusions are actually the things I talk about in the first lecture of a class I teach in water policy, a graduate class that's cross-listed in multiple departments, including law, and I know many of you are lawyers here. And so this is a slide I use it in presentations like this as well as my class, that water policy reflects many determining factors. And I list some of the obvious. Obviously, this is not an exhaustive list, but I underline a few. And I underline these in all presentations, so I haven't added the underline just here. And that is what you see depends significantly on the legal framework. And also that what you see in policy reflects the actions of many, many players and decisions of many players, and can reflect the extent to which things are centralized versus decentralized or fragmented. And those are important things because this whole issue of logic and understanding what goes on in the physical isn't always what we see in the actual legal. And so the importance of context has to be underscored, whether it's the physical context, the geographic, the way the governance is set up at the higher level. So I've been using the term governance. What do I mean by groundwater governance or governance? And this is one of those things, if you start researching what is the definition, you'll find about as many definitions as there are papers written on it. And some of them are paragraph long. Some of them are multi-sentences. I saw somebody, I didn't put it in here, who actually did a very nice job in making it an even shorter sentence than the one sentence I offer here. But this groundwater governance is the overarching framework of groundwater use laws, regulations, and customs, as well as the processes of engaging the public sector, the private sector, and civil society. Now, it's a long sentence, but at least it's just one. That was a goal when we were writing this paper that was published in Groundwater a few years ago, We wanted to get it down to one sentence. And the important thing is that governance is not the same as government, okay? So government carries out the laws and enforces them and so forth, but governance is more than that. You could see it's processes. You know, governance, how do people get involved? Are things bottom up, top down, and what is the involvement? And notice we use the word civil society, which isn't used that much in the US. It's more of an international term of kind of everybody out there, kind of the people and so forth. And then a lot of times there's this, let's say, lack of clarity or confusion or just interchangeability of talking about governance and management. Lenny had in his slide, we need to improve our management of groundwater. And I just simply say groundwater management is the what we do. And so the example I'd like to use, which is an Arizona example, is that, and it's just one of hundreds, is we have a legal framework relating to water banking and storage and recovery, recharge and recovery. And so we lay out kind of enabling mechanisms, but then it's up to the water suppliers, the water providers to decide how they do it, what they want to do to take advantage of that framework. And so that's the management. Are we delivering Colorado River water to our cities in Arizona through treatment plants and direct delivery as they do up in the Phoenix area, or are we basically treating our surface water and delivering it through storage and recovery as we do in the Tucson area? So that's an example of the difference between, as I see it, governance and management. So I mentioned that we did a survey back in 2012-13. We called it an initial survey. And we have a report on it, and I have our website in my last slide that has the connection to our link to our page on groundwater work. And we were being ambitious or maybe optimistic when we called it an initial survey. First of all, it was self-funded, it was very limited, and we did it in a short period of time by surveying a single water official in each state to get a sense of the lay of the land. And it tended to focus more on quantity versus quality. And I'm going to, in a moment, show you just a few slides of results from that survey. And I put up as just a first graphic was one of the things we asked was, do separate agencies deal with water quantity and quality? And in most cases, the blue, we see that separate agencies deal with those, but not in all cases. And sometimes things change. So this was a few years ago, and things may have changed. And what's interesting is that, and we asked about this in the second survey a little bit, you know, there's sometimes good coordination and communication, but many people think that the coordination and communication between agencies, even in a given state, could be improved. But often there's not as much coordination and interaction across similar type agencies across the states. And in fact, when I showed this slide a number of years ago at an Arizona conference, somebody from the Water Quality Agency said, oh, that was really interesting. I didn't know that there were so many states that had it separate like we do in Arizona. And then we did another survey that was funded by the Groundwater Research and Education Foundation, which was completed in 2017, and that focused more on water quality. And in fact, this is a snapshot of a publication that was just published on Tuesday in the journal Water. One of our co-authors, Mike Wireman, who's on the board of the Groundwater Research and Education Foundation, lives here in Boulder, is here in the room. And as you can see, we entitled it Critical Issues Affecting Groundwater Quality, Governance, and Management in the United States. And so I'm going to show you 3 slides of results from that first survey, followed by 3 slides from the second survey. So this depicts the groundwater governance priorities that were selected. You know, just what are the groundwater governance priorities of your state? And you could see that water quality or contamination is very, very high. 45% of the states indicated that. And our second survey basically reinforced that. Interestingly, conflicts between water users showed up as the second most frequent. Yeah. Again, this is one person's response, so you can't take this to the bank, but declining groundwater levels And then you can see a number of other things following. And then this slide, I actually haven't been using this slide, but I decided to put it in here. This is a slide of does state law recognize the connection between surface water and groundwater? And so the yeses are the blues, the nos are the yellowish, and no answer from a few states. And the reason that I haven't been using it is that when I did show this at a meeting of the Groundwater Protection Council shortly after we did this, and there were some people in the audience, and it was some people from Nebraska, who said, well, your answer for Nebraska is wrong. Anybody here from Nebraska? Your answer is wrong. And I said, oh, well, that's the answer we got from a state official. But after that, when I saw some other people from Nebraska, I kind of probed it with them. Kind of the answer you get depends upon whom you ask. Because of the way they manage their resources there, surface water is kind of done in one way and groundwater is done in another way, and it depends who you ask. So we realized that this is an example of a complex issue that requires further investigation. We really haven't been able to delve into that further. And like I said, I typically don't show this, but I'm glad I put it in given how much discussion we've already had just from the first two speakers about the interface. And so it's very frustrating. The law is not recognizing the interconnection, but actually even when the law doesn't recognize the interconnection, and I have no idea what my colleague Jim Hallway is going to talk about Arizona, but it's an example where even though the law doesn't recognize the connection, policies and management, in a sense, are integrating the two. And in fact, that's why those numbers on Lenny's slide, where if you look at the overall depletion, it's one thing, but then if you look at the intensity of it, it's changing in there because of some of the policies that we've implemented in Arizona. And then this was the slide I showed earlier that I said I was going to come back to. And so this is showing in blue the states that say they don't have sufficient regulatory capacity to enforce their groundwater priorities. The gray are the yes, and then the hatch marks are the states that identify declining groundwater levels as a priority. So you can see in the West, a lot of answers saying no, but again, by the person responding to it. This is also reinforced in something I'll show you in a minute from the second survey, and it's not actually surprising. It's a function of resources as well as what the legal framework might say. But you see some interesting patterns there. You even see states that identify declining groundwater levels as a priority, some of those northeastern states and other places that aren't bad off when you look at what's happened with depletion and the like. So here are some slides that come from the second survey, the one that we completed just a year ago, just published. We're just putting the survey report now online, and the paper's an open access paper. And any of you who publish know these days, if you put your stuff online too fast and then you go to publish it, the journals don't like that because your stuff's already been publicly available and so forth. So we had to kind of keep it, we distributed it to people who wanted it, but we didn't put it online. But here's the frequency of groundwater concerns listed in the top 3 by states. And so you see quality, again, is listed by a lot. You see quantity there. And then you see budget. Yeah, oops, that's what budget and personnel, they're, of course, connected as, again, capacity issues being of concern. And then this is the #1 ranked groundwater concern. And again, this is the mosaic here. And you see the states that showed quantity, Arizona, California. Interesting, Washington. And then quality is the light blue and the like. So differences. And then this is likely issues requiring attention in the next 10 years. And monitoring the increased groundwater pumping, water level monitoring, as well as quality, and you can read across it. Climate change is up there, and interstate conflicts, industrial waste. Again, these are what are on the horizon. So, general conclusions are we had some interesting state level similarities, differences, but as I said, you don't want to go to the bank with some of this, but it shows you some of the trends and so forth. We obviously need some more research for validation and interpretation. It's difficult to do more than descriptive reporting at this point because we don't have that kind of richness of multiple responses for a state or responses over time for a state. And then I already mentioned recognizing the surface water, groundwater, and then the evaluation of success or lack of success in achieving policy goals. I mean, that's really the crux of this, is we can look at a lot of things, but what's working and maybe what's not working, and what can we learn from each other? And I'll have a few more words to say about that toward the end. Things we'd like to look at also are the state laws and practices concerning managed aquifer recharge. That's gotten so much attention in California because of what Lenny showed, and this whole idea of you got water in the winter and maybe you could use those farm fields to increase storage and the like. And then, of course, there's case study analysis, and that's what we're going to be moving into at the conference here and hearing very interesting case studies, and I'm sure some successes and also some challenges. I wanted to mention that case study analysis is always interesting, but sometimes it can be difficult to glean out what are those common threads that we can learn. We did a case study, looked at 3 different cases, one in Arizona, the Orange County Water District in California, and area, the Orlando region of Florida, that were all dealing with regional water issues. And we came up with some conclusions about, obviously, the water needs of the region in the context of the legal framework, already covered that. We noted that robust stakeholder engagement was key to successful regional groundwater governance and management. And then sharing best practices is good, but recognizing that groundwater is a very local resource, this whole idea of bottom up, and all the work of Eleanor Ostrom and many others looking at the importance of approaching these things locally with the users. Wanted to just mention very briefly the whole concept or the issue of transboundary groundwater, and that brings into it a whole additional layer of complexity because, again, what level of government, what are the mechanisms for governments to cooperate, and between Mexico and the US, it becomes a diplomatic issue necessarily involving the US. Has anybody read the recent Western Governors Association statement about the involvement of the feds in kind of water stuff? About a month or so it came out. Any of you get that monthly or maybe weekly thing? It's like, don't mess with us. This is a very, very, this is a state issue. And so when it comes to communities, and this is a graphic, I've been working on a US-Mexico transboundary aquifer assessment program, not a governance program. It's all about assessment. And we've been looking at 4 aquifers along the border. We're only talking about assessment. It's complicated enough just dealing with the local situation. Even in Arizona, one of those aquifers is in an active management area where we actively manage groundwater. One is outside of it. And then you add the layer of the federal government. Will you get to a point of being able to ever talk about management of groundwater when you have communities that are 100% dependent on groundwater? And they're in the bullseye of warming, changing precipitation patterns, growth, all those things. So complex issue with tribal nations, also a complex issue. There's a conference coming up in just a month from now, American Water Resources Association conference, focusing on this whole issue of transboundary groundwater. So returning now to the title that I was assigned about the conundrum. And so, you know, the conclusion is there's no recipe for achieving sustainable groundwater management. You know, you're going to have to figure it out. But there is definitely value in sharing the lessons learned. And there's a very nice book that was published. It's also probably pretty expensive too. The Advances in Groundwater Governance that came out at the very end of last year that includes 30 or more chapters. We have a chapter in that on the US in this mosaic issue. But they, at the preface of the book, even say the book does not present final conclusions or recommendations, as no silver bullets exist for groundwater governance. But I don't think we should be too discouraged by that, right? Because if it were easy, it would all be figured out, and then we wouldn't have reasons to get together to talk about this over a 2-day period and kind of exchange ideas and so forth. So I don't think we should be discouraged by that and see it as an opportunity for contributing and helping improve the situation, because there's no shortage of need for doing so. So with that, I'd like to thank you. I'd like to thank my many collaborators in the projects, too numerous to list and mention. And just note that I've put a couple of links up there, including a link to the columns that I write that I sometimes in a page or so talk about these issues. So thanks very much.
Why don't, since we're running late and we're